Keine Angst, keine Angst. Kalt rausgefahren, ja. All right, ladies and gentlemen, shall we start? No. Nonetheless, there will be an exam. There will be a written exam. The exam will be on February 16th. This is a Thursday, the Thursday during the exam week, during the regular lecture hours, that is 2 to 4 p.m. Does anybody have serious trouble with that? I'm well aware that this is the same day that Theory 3 lecture, PDP 3, will have their exam in the morning. Sorry, Anna. Nonetheless, I think it's the only possible time for us if we want to have the exam still during the lecturing period, which I would like to have. So I will send an email to all of you through the lecturing system, asking you to confirm whether you would like to participate or not in the exam, just for us to know how many approximately we can expect, because that of course calibrates the room that we need and the number of handouts that we print and so on. If you then decide, oh no, I'd rather not do that, just tell us. It's just for us to have an idea. So much for that. Is there a serious problem with that? Please say no. Thank you. Next thing, and this is embarrassing, again, I will have to run away at the end of this lecture because I have an appointment with the Deputy Rector for teaching. And I think that some serious matters of our curricula are under attack, and I need to go there. Nonetheless, this is the last lecture where I want to present new material. And I think we will finish a little bit earlier today. So I hope this won't cause any problem either. Please say no. Okay. Good. Do we have any organizational questions on these matters? Yes, of course. Good question. I will be here. And what I would like to do is, if you are interested, to go through the whole material again, to maybe order that, give an overview of what we did, and maybe answer questions that you may have. I can't ask today. Yes, so I will be here, and yeah, if you want, pass by, and if you don't, stay away. As always. All right. Yes, thank you. That's something I should have said. Okay, now what did we do last time? I wanted to make you aware of the mean field approximation, an approximation that you often find in suitable situations, and I told you what the situation have to be, what the situations have to be like in order for a mean field approximation to be successful? Namely, you must be able to neglect fluctuations that are introduced by microscopic degrees of freedom. And if you can do so, and I argued why I believe that we can do so, then a mean field approximation is always something worth trying. And we tried with a crude version, admittedly crude version of the mean field approximation, and it worked like a charm. And this is why we kept pursuing the mean field approximation. And there are, of course, refinements that we are currently looking at. The big thing about the mean field approximation is, of course, that then you can take particle interactions into account without a perturbative ansatz. And since I showed you the perturbative ansatz, I think you have an idea that this is something that you would like to avoid. Good. At this point, I should mention that I heard from Celine, your tutor, and Philip as well, that you are lagging a bit behind with the problem sheet, which was very welcome to me because then I did not have to invent a new one. Nonetheless, I did invent a new one, which you may look at or not if you're interested. And this also goes in the direction of refining the mean field approximation. So if you want to have a look at how this refinement could proceed, maybe that is a problem sheet that is also interesting. And if you like, we can, for example, discuss this next week. So there is a problem sheet. It says that this is to be discussed on February 1st. I handed this out on February 2nd. If you have trouble with time travel, we'll solve these problems next week. Okay, do you have any question concerning the mean field approximation? Okay. You're nodding but not showing up. Okay, I know the reason. Good. Yeah, I would like today to go through another important part of possible cosmological applications of kinetic field theory, namely velocity power spectra. So like density fluctuations, you can cross-correlate velocities, velocity perturbations. Why is this useful? Let me give you a few reasons, but first of all say what this is. So if you cross-correlate densities, you cross-correlate two scalars, and the result is a scalar correlation function. Not the case, of course, for velocities, because there you correlate a three-dimensional quantity with a three-dimensional quantity, and you get a 3 by 3, that is a matrix-valued correlation function. And so the velocity correlation function is a matrix. If you think of this matrix in linear approximation, which is, of course, not what we would ultimately like to look at, then you see some important things. So we introduced the velocity potential psi, and we saw that there is, in linear perturbation theory, a relation between the density fluctuations and the velocity potential, which says that the Laplacian of the velocity potential is the negative density contrast. This is the Poisson equation satisfied by the velocity potential. And we often used already that the power spectrum of the velocity potential is then given by the power spectrum of the density fluctuation divided by k to the power of 4. K is the wave number. And of course, k to the power of 4 comes because that squares the Laplacian in Fourier space. Laplacian in Fourier space is minus k squared. So this is just the squared inverse Laplacian applied to the density fluctuation power spectrum. Now, this is really important because you see, first of all, it falls off very steeply with k. The cold dark matter power spectrum, for example, has a k to the minus 3 fall off. So the velocity potential, the power spectrum velocity potential goes like k to the minus 7 in this case. Falls off extremely steeply. In other words, the fluctuations that you expect in the velocities are of much larger scale or have very much lower level of small scale fluctuation than the density fluctuation. So if you, for example, could measure the velocity power spectrum you would have access to much larger scales, and therefore much more linear scales than in the density fluctuation power spectrum. Or another way of looking at this is that scales that become nonlinear in the density are typically much less nonlinear or even still linear in the velocity power spectrum. So this is a very important piece of information. Then another reason is that in general relativity, you have two gravitational potentials, which are where one is the negative of the other. And if you compare this to the Newtonian case, you find that the Newtonian potential is just one of them. Now, in general relativity, the propagation of light, for example, is controlled by the gravitational potential. But in other theories of gravity, these two potentials do not need to have this simple relation that one is the negative of the other. They could be different. Now, the propagation of light is controlled by the sum of the two, or rather the difference, while the propagation or the motion of material particles, of the motion of particles which have a finite rest mass, is controlled by only one of them. So typically, alternative gravitational theories that are not necessarily equal to general relativity predict the different behavior for material particles than, for example, general relativity does, or Newtonian gravity would. So this means that because of, for that reason, the velocities contain also important information on deviations of the underlying gravitational theory from general relativity, and so on and so forth. So there is important information in the velocity power spectrum. All right. Yeah. I told you before that, let's fix this right now. If you cross-correlate a linear velocity in this case, which is just the gradient of the velocity potential, then this is the velocity power spectrum, or the velocity cross-correlation function. And you see that there's this vector product or a tensor product in between, which tells you that this is a 3×3 matrix. Right? So what you cross-correlate is every component of the velocity at one place with every component of the velocity at another place. Right? So of course, this cross-correlation function here is also controlled by the separation of the 2 points that you're looking at. Right? You pick out one point, you look at the velocity there. You pick out another point, you look at the velocity there. And now you cross-correlate all components of the velocity here with all components of the velocity there. And the result will be a matrix-valued correlation function controlled by the separation of these 2 points. All right. Now, you cannot directly compare this to a power spectrum for the density fluctuations, for example, because it's matrix-valued. But suppose you take the divergence of this. Oh, sorry, that was nonsense. Suppose you take the trace of this matrix, and suppose you do this in Fourier space. In Fourier space, this would translate to the average of the two velocities. The average of the two velocity potentials times the tensor product of the wave vector with itself. And here you see, if you now take the trace, you get a factor of k squared, and then this is the density fluctuation power spectrum divided by k squared. So of course, the two are intimately related, right? But the measurement of these quantities and what these measurements tell you gives access to different type of information than the density fluctuations alone do. All right, but how do we access the velocity in KFT? We spoke about the construction of the generating functional in KFT. And one of the key points that we were looking at was that we studied the propagation of particles in phase space. So we gave the particles a starting point in phase space, and then we pursued the trajectories through phase space. In other words, the information about the particle velocities is automatically contained also in the KFT generating functional. But how do we get it out? In exactly the same way as we did with the positions, right? If you think of the of a one particle density operator that we applied in Fourier space, this this was the exponential of minus I, and then the functional derivative with respect to the positional component of the J source field. And of course, we also have momentum component of this source field available. Right? We could equally well take a functional derivative with respect to the components Jp. And then you get a momentum, and you get the momentum of particle J. Okay, then you don't know where particle J is. And that's a bit of a problem, right? Because if you only apply the functional derivative with respect to Jp, what you get is Pj. You have no information at what location this Pj is. So the only thing that you can expect from KFT would be a combination of spatial information and momentum information. So you will always have to ask, where is this particle and what is its momentum? And therefore, what we define in KFT is a momentum operator, capital Pi hat. And this is a combination of a density operator, which tells you where the particle is, and a momentum operator. So again, let's introduce a one particle momentum operator, the index J. Let's give it a wave vector K1. And remember, this is notation saying that we are applying this operator at a time t1 and an operator with a wave vector k1. So this we define as minus I now a functional derivative with respect to the momentum component of the source field taken at time t1 combined with the density operator of the same wave number and the same particle. That's all we can do, right? Because if we only take velocity or momentum information from KFT, then all we get is a momentum, but we have no idea where it is. It's almost like in quantum mechanics, right? That's an interesting relation here. Once you know the momentum in quantum mechanics, you're sure, if you know it precisely, you're sure that you have no idea where it is. All right, now what does this mean? This is, in fact, in view of cosmological applications, a very welcome quantity. Because what you can usually measure is not the velocity of something at an arbitrary position. But of course, what you can measure is the velocity of something which is an object. And objects are there where the density is high. Right? So what people actually measure in cosmology is exactly this thing. Right? Because the probability of finding a thing, this one, is automatically contained in the selection criteria that you do apply in cosmology. So in fact, if you ask, let's say, a common cosmologist from the store, the common cosmologist, what kind of information they would like to predict or would like to have predicted by theory is exactly this quantity which KFT gives you automatically. Lovely. So we have no trouble with that. Okay. So this is the thing that we introduce as a momentum operator, and what it gives you is a combined information of density and momentum. Okay. Now suppose you want to take arbitrary correlation functions of momenta, then what we do is exactly what we do with density operators. And we start with pi applied to particle J1 with wave vector K1, and we go to JL, if L is the order of correlation function that we are looking at, of L, and this is applied now to, for the moment, the free generating function. I'm neglecting particle interactions today. Okay. So this is what we want to extract. This is a velocity or a momentum correlation function in the sense of this momentum operator that we have here. Now you see, the momentum part of this operator acts on Jp at a different field than Jq that the density operator is acting on. So in other words, you can reorder these operators and first apply all the density operators that are contained in this sequence of momentum operators here. And they will, of course, do what they always do. They will create a shift. And then you will have, I like this combination of indices, right? J, P, J1. You apply this sequence of functional derivatives here to Z0 of J plus L. Yeah, the density operators will create the shift L. Therefore, Z0 will then be evaluated at J plus L. And then we need to apply the further functional derivatives that are contained in here. Okay, that's the procedure we have to apply. And in fact, since every action here, every functional derivative here returns a vector, this product here is in fact a sequence of tensor products. Right? It's a vector multiplied with a vector multiplied with a vector. Okay, but then if you look at what Z0 was, Z0 of J plus L, then this was the integral over the initial conditions times this phase factor here, where now J plus L appears instead of J or L only, and where I have specified the free trajectories only for simplicity for today. All right, now you see, I can easily replace the J derivatives with respect to Jp, by derivatives with respect to Lp. And they will have exactly the same effect. That is, they will pull down the momentum information from the particle trajectory. Right? So in other words, given the structure of the generating functional, I can also replace the derivatives with respect to Jp by derivatives with respect to Lp. No problem with that. So this means that I can write the whole sequence of steps here in this way. With functional derivatives with respect to L apply to Z0 of L only, and J is completely gone. So in other words, again, we are back to the task of evaluating the free generating functional. You know how, right? Because we factorized it and decomposed it into standard factors and so on. And then all we have to do is take a suitable number of functional derivatives with respect to the L vector here. Good. Okay. Now then we will have a velocity power spectrum and everything will be fine. Now let's have a look at what happens if we take L equals 2. So in other words, if you want to take if you want to extract the simplest statistical information that we can pull out, namely the cross correlation function in Fourier space, the power spectrum of the velocities. Okay, so let's now fix L equals 2 and yeah. The structure of the generating function here tells you that instead of taking functional derivatives with respect to J, you can equally well take functional derivatives with respect to L. But the procedure is that once you are done with applying these operators, you set J to 0. So this means that you can set to 0 right away. Sorry, you can set J to 0 right away and replace these operators directly by functional derivatives with respect to L. All right, L equals 2, then you know very well what the shift is like, right? The whole shift is then minus K1, 1, 0, delta B, T minus T1 times E1 minus E2. That's the shift tensor in this case. We had this so many times that I think we don't need to go through that again, right? All right. So I know that this scalar product here is just LQ times Q initial plus LP times P initial. This is still a bundle of all the initial positions and momenta. And Q is minus K1 times E1 minus E2, and LP is minus K1 T1 times E1 minus E2. Do I need to explain this again, or are you happy with that? Moderately. All right, that's what we know. Yeah, and then if I apply this here, I'm getting minus K1 times Q initial 2, 1 minus Q initial 2, minus K1 T1 P initial 1 minus. All right. So far, so good. So now this means that I can write Z0 of L in the form still need it that way. Okay, integral over d gamma as before. E to the minus a half LP transpose CPP times LP. CPP is the cross correlation matrix of the initial momenta, and e to the I k1 times r, where r is the separation vector between the 2 points that we're looking at. All right, and yes, the integral over p and q remains here, just because now we will have to take derivatives with respect to LP. Good. So I'm introducing a quadratic form, which is minus a half LP transpose times CPP times LP. And now, of course, I can instantly apply these further differentiations that I need to take in order to get the velocity power spectrum. Good. So what we need to do is to apply minus d1 tensor d2, where capital D1 is the derivative, the derivative with respect to LP J1. Derivative, functional derivative with respect to LP J2. Okay? Yes. About it. Yeah, I don't want to carry out the momentum integral as we usually do, because I still need the LP components here. Right? And the gamma was just a multiple integral over all the dRs, the relative coordinates in configuration space, and an integral over the momenta. But I don't want to carry out the integral over the momenta yet, because I still need the LPs here, which would otherwise be replaced by. Am I talking nonsense? No, I don't think so. No, that's fine. Okay, good. Yes. Okay. So what I have to apply is these derivatives to e to the power of q and times the Fourier phase factor. And since only the q's depend on LPs, we have minus d1 tensor integral d gamma d2q e to the power of q e to the I k1 times r and this is going to be integral d gamma d1 d2 q plus d1 q times d2 q e to the power of q e to the I k1 times r. And there should be a tensor product in between this, right? This is the result is going to be a matrix, same as here. Okay, suppose the information in parentheses would not be there, then you would have the ordinary density power spectrum. That's the only difference. Okay, now you see the second order derivative of q will just leave a factor of minus. The 1/2 will be gone because we have taken the derivative of a square here in LP. So it's going to be minus CPP. And since we are taking the derivative with respect to d1 and d2, it's going to be minus CP1, CP2, minus CP1, d2. A function that we very well know. So this is the matrix CP1 minus CP1, d2. All right, and if you look at d1q, that's going to be minus let me write it this way, right? Minus CP1 P LP. So this consists of minus CP1 P1 times LP1 plus CP1 P2 times LP2. Right? And the same, of course, for DQQ. So what is this? That's just the velocity variance, right? It's the correlation function at zero lag, right? At zero distance between the 2 points that we're looking at. And LP1 is minus K1 T1. So we will have plus this. So that's a vector, of course. And then we have to add minus CP1 P2 times LP2, but LP2 is plus K1 T1. Right, so we will have this result here. Or in other words, CP1 P1 minus CP1 P2 times K1 T1. Okay. What happens if you take the derivative with respect to LP2 first? Then you have a CP2 P1 and the two are symmetric. So you get the same result. Yeah. Maybe let me write this down. Here, P2Q, CP2P, LP. So that is P1. So this is K1 T1 negative. And you get plus, minus CP2 P2 LP2. So this is K1 T1. And you see that you just get the negative of the other one. So this is minus D1Q. Okay. So the whole result is that you need to integrate over the momentum cross correlation and minus CP1 P1 minus CP1 P2. This is a matrix. times the vector k1 t1 squared in the sense of a vector product. And you take a vector product of this vector here with itself. Times all the rest that you also have in a density fluctuation power spectrum. Okay, now you see this term depends on time. This does not. So ultimately this one will win, and you can still simplify the velocity power spectrum. All right, this is what I wanted to show you about the derivation of velocity power spectra. You see that we introduce, as usual, an operator for the quantity we need. This time we need to have a combined operator that consists of a density operator that tells us where a particle is, and a momentum operator which tells us what momentum this particle has. And then we can, by application of suitable numbers of these operators, calculate power spectra as we like. Okay? Yes. Sorry, there's just shorthand notation because I was running out of space here. What I mean is, so square in the sense of the tensor product. Okay. No problem in principle, or is there one? Now, what I would like to show you is something that completely puzzles me. Okay. Take this innocent power spectrum here, where, as you saw before, the only change with respect to the density fluctuation power spectrum is that expression here in the bracket. Now, what about the asymptotic behavior? We developed methods 2 weeks ago about studying the asymptotic behavior for very large wave numbers of expressions like that. So what's going to happen if we do the analysis of the asymptotic behavior now for the velocity power spectrum and not for the density power spectrum? And the changes are in fact minimal. Remember, we had to decompose the Fourier part from the rest, and we applied a standard technique to integrals of that sort. And of course, we can now do the same, exactly the same thing for the components of this velocity cross-correlation matrix. And the only thing that's going to happen is that the function g that we defined while we were looking at the asymptotic behavior. Remember, we had a function e to the power of minus lambda f times a function g. That was the starting point. Then we specialized the function g, small g, to be the Fourier phases. Now, if we want to do the asymptotic analysis with this expression here, the only thing we have to do is replace the function t, which used to be the Fourier phase only, and the Fourier phase times this expression here. Okay, are you with me? We had things like this. Right? And we looked at the asymptotic behavior of absolutely convergent integrals over domains omega here of that sort. We generally looked at this and then specialized to what we call Laplace Fourier type integrals, where g is the Fourier phase. And in the whole analysis, a function capital G was important. And the capital G was essentially the small g after a suitable coordinate transform. and we needed the derivatives of this function capital G, and then the leading order powers of the wave vector that appeared in these derivatives of the function G. Right, so we had to look at the function G that was this, right? There was a diffeomorphism H involved that transported this onto a suitable coordinate system. We didn't care very much about this. We just used Morse's lemma to ensure that such a diffeomorphism existed. Then we needed the Jacobian of this diffeomorphism, and we knew that the Jacobian evaluated at the minimum point of F was just unity. It was just the unit matrix. And then we needed the derivative to some gorgeous order here of G taken at the minimum position of the function F. That's what we needed. And then we said, okay, good. Now, if you apply a Gaussian derivatives, Gaussian is a very, very finely defined quantity. Right? If you apply a Gaussian number of derivative operators to the function G, essentially you apply all these derivatives to this exponential factor here, and you get an enormous polynomial of k vectors and the exponential factor. And the highest power of the wave vector k that will appear is always determined by applying all these derivative operators directly, not to the preceding polynomial, but directly to the Fourier phase factor. And therefore, we didn't care very much what else there was, possibly in front of the exponential here. But we knew that every derivative of the phase factor would give us another power of k. And so the highest power of k that we would get would be alpha. And exactly the same way of reasoning applies now, right? Because we are just decorating the Fourier factor with something else. And now we need to make sure that the same argument that we applied here, namely that if you count powers of k, the derivatives applied directly to the Fourier phase factor give you the highest number. Now, is this the case? Well, let's see. But the idea is really very, very simple, right? We saw this asymptotic analysis, and complicated as it was, there was this one crucial step concerning the function G, namely, you apply all the derivatives directly to the Fourier phase factor and you get the highest power of k. And what I would like to convince you of now is that regardless of this prefactor here, its properties are such that the same arguments apply. And then this means, of course, that the coefficients that we had in our power series, in our asymptotic series, would have the same dependence of k as before. And this turns out to be true, because their amplitude is changing by some amount which is completely irrelevant. And this means that if you do the asymptotic analysis now of the free velocity power spectrum, the free velocity power spectrum asymptotically will go like k to the minus 3, such as exactly in the same manner as the density power spectrum does. And this is completely unexpected. Right? Remember what I said in the beginning about the velocity power spectrum. But, for example, for cold dark matter, it should go like k to the minus 7. In other words, it should fall off like k to the minus 4 times the fall off of the density fluctuation power spectrum, as long as linear fluctuations are relevant. But this analysis, or these arguments that I gave you now, show that very, very quickly, if I have a freely evolving, freely streaming collection of particles starting from a Gaussian random field, also the velocity power spectrum will enormously gain in power on the small scale, and will very quickly fill up the k to the minus 3 times. In other words, the nonlinear behavior is dramatic here in the velocity power spectrum, much more dramatic than it is in the density fluctuation power spectrum. And the expectation that you have from linear theory is completely wrong. Right? You would expect from linear theory that the spectrum, the velocity power spectrum, falls off like k to the minus 7 in cold dark matter, for example. And it doesn't. It falls off like k to the minus 3 very, very quickly. How can I say very quickly? Well, remember we made a time analysis of the asymptotic series and the evolution of the asymptotic series, and this turned out to be very quick. Okay, this is something that is completely puzzling me. Right? First of all, this means that First of all, this means that linear expectations on the velocity power spectrum are completely misleading, even though you would expect velocity fluctuations to retain their linear behavior for a much larger time, because their spectrum falls off so quickly. Not the case. Not the case. Right. And second, it tells you there must be a mechanism in the free streaming, right? We haven't taken any interaction between the particles into account. There must be a mechanism in the free streaming that immediately fills up the k to the minus 3 power in the spectrum. Yes, Alex. Could be. Could be. I don't hope so. They should. They should, because essentially you're applying the free generating functional by a mean interaction factor that has no L dependence, no LP dependence. So yeah, it should, but I don't really know. Okay, now let me try and convince you that this whole argument is in fact true. Right? That if you apply derivatives not only to these Fourier phase factors, but to the complete expression consisting of this term in brackets here times the Fourier phase, but still you get the highest powers of k by applying the derivative operator directly to the Fourier phase factor, not to everything in front. That's what we have to check. And how do we check this? Well, we'll see. But you see, the argument is really straightforward. The conclusion is completely puzzling. Okay. So we are talking about an asymptotic analysis. And what you see from this expression that we found in the asymptotic expansion that we had earlier is that we need to evaluate the function here near the minimum of the function f that appears in the exponent. And that means that we have to take the small scale limit of all these correlation functions here. Okay, now, what exactly were they? We had CP1, P2 is minus A1 of R, and R is the separation between the 2 points, 1 and 2, times the unit matrix minus A2 of R times the parallel projector on the separation vector between points 1 and 2. Now, of course, these matrices here just give the correlation function some orientation, which doesn't matter for our asymptotic analysis. So all we need to look at is the asymptotic, and that is now the asymptotic evolution of these functions a1 and a2 for small r. In other words, we can make a Taylor expansion in R of these functions a1 and a2. Now, what were they? Confusingly, they are 2 minus sign. This is a choice that was specifically made to confuse you and myself. So what remains is a k-space integral here, but this is an integral over wave number only, not over wave vector. This was a1. And here I missed the chance of confusing notation because a1 goes like j1 and a2 goes like j2. It would have been much more effective to rename the two, but I missed that particular chance. Okay. Now we can use the Taylor expansion for the spherical bezels, which is given by chain u of z equals z to the power of mu times the sum from k to infinity over minus z squared over 2 to the power of k divided by k factorial 2n plus 2k plus 1 double factorial. Yeah, that's how it is. So j1 of z, u is 1, so we have z times I'm sorry. Repeat. Yes. Now for k equals 0, you get 1, 1, 2, plus 0 plus 1, so it's 3 double factorial. So it's 1 over 3. Now for k equals 1, you have minus z squared divided by 2, 1 factorial, 2 plus 2 plus 1 is 5. So it's 5 double factorial or 15. And so on and so forth. That's all we need for now. So this is z over 3, 1 minus z squared over 10. Okay, and j2 z squared from that factor. Now for k equals 0, again we have 1 divided by 1. Now we have 4 plus 0 plus 1, so it's the 5 factorial, 5 double factorial right away. So it's 1 over 15. And lots of things that I don't care. So if I now return there, this is approximately, and now you see here the z, which is a kr, is divided out instantly. And we get minus 1 over 2 pi squared integral over dk d delta of k. The prefactor 1/3 applies to all. And we have 1 minus kr squared divided by 10. Okay. Now you see, we have an integral over p delta. That's what we usually call sigma 1 squared. So we have minus sigma 1 squared over 3. And then we have an integral over k squared dk. That's what we, times the power spectrum, that's what we usually call sigma 2 squared. So we have now minus sigma 2 squared divided by 30 times r squared. That's this function here. Huh? Yes. Okay, now if you look at that here, it gives you a factor of k squared r squared right away. So again, we have an integral over k squared d delta of k, that's sigma 2 squared, times r squared, divided by 15. Okay. And so forth. Ah, indeed. Indeed, yes. Thanks. Okay. So now we can insert these approximations, these Taylor approximations, into this place here. Then we get a term that is constant in Q. Right? Because here, for the CP1P1, R equals 0. We don't even need the Taylor expansion, and this is just a constant. So any derivative applied to that won't contribute anyway. So the only term we need to be careful about is this one, because this gives us a power of k squared. And this could change the asymptotic behavior. So again, we have a constant term here. Which does not contribute once we take the derivative with respect to q. And then we have this term only, which gives an r squared times k squared. Now you take a derivative with respect to r, and the factor of r is remaining. But we have to evaluate it r equals 0, so this is gone. Right? And only at the next derivative with respect to r, we would enhance the power of k by 2. But this means that we only add a constant to the highest power of k that appears here. So it is the fact that here you multiply k squared with an r to the power of 4 that is responsible for the fact that the asymptotic behavior of this function capital G is unchanged. This is what I wanted to illustrate to you. Right? Whatever is out front here has sufficient power in Q such that after a suitable number of derivatives, terms will either disappear or contribute at most to the same power of k that we already have. Okay. In other words, the asymptotic power spectrum, asymptotic fall off of the power spectrum, is not going to be changed if you apply the same asymptotic analysis, and it falls off like k to the minus 3. And the amplitude is going to be changed by minus sigma 2 squared divided by 3, and nothing else is going to change. Right, so we know that, let me write this down here, the nonlinear power spectrum for the velocities is asymptotically going like minus sigma 1 squared divided by 3 times the density the nonlinear density fluctuation power spectrum. And in other words, this is going like k to the minus 3 as well. All right. I know this was a rough illustration and not a derivation, but I think the overall argument is clear. Or isn't it? I mean, if you like the fun of going through these derivatives of the whole function t, that's fine, but I think this is inappropriate for a lecture. I mean, you can do this on your desk much better than you could do this on the board. And watching me doing this on the board is going to be boring. All right, convinced? Okay, now another point that I wanted to address is we have always neglected initial density and density momentum correlations, also in our consideration of the asymptotic behavior of the power spectrum. Now, was this appropriate or was it not? Can we expect the asymptotic analysis to go through as well if we take initial density and density momentum fluctuations into account? And this is a question we still have to address. All right. Now again, in order to not bore you excessively, let me sketch the calculation. And if you want to see the complete calculation, then you can follow it in the script and the lecture notes. So remember how we calculated our initial probability distribution. We introduced a characteristic function, because with this characteristic function, the whole subsequent calculation became much easier. And with this, we calculated the probability distribution for a data vector D. Then, in order to take the density and density momentum fluctuations into account, we had the differential operator d hat that d hat divided by v squared that we needed to apply to this integral here. But then we needed something for this density operator, for this derivative operator to act on. And we call this S, vector S. So this derivative operator here acted on components of S. And how was this defined? Well, d hat was 1 minus I ds1, 1 minus I TDS2. You remember that? The whole sequence of steps was we needed a probability distribution for density and momentum fluctuations, and we needed to convert this probability distribution for the density fluctuations to a probability distribution for finding particles there. And this is how this operator D hat came into the game. All right, now the data vector consisted of density fluctuations at points 1 and 2 and momentum fluctuations at the same point, and the characteristic function was the exponential of -1/2 T transpose C times T and C was the covariance matrix of the data vector. Just repeating that, and we went through these arguments in rather long detail. And finally, the S here consisted of S1, S2, and zeros, right? Because the only function that these S components, or that the S vector had, was that by taking derivatives with respect to the S components, we wanted to take density fluctuations down from the exponential. So this operator represents 1 plus delta 1 times 1 plus delta 2, and these are the probabilities that I need in order to convert density fluctuations to particle number density fluctuations. Okay? So far, so good. Now, a whole machinery starts, and what we said initially was that, well, I don't care about D hat, because later it turns out that the initial density and density momentum fluctuations are subdominant anyway. Okay, that is acceptable at late cosmological times, but it may change our asymptotic analysis. Okay, so this time we need to leave D hat in, but then we also need to leave S in. And this starts a whole mess. And, well, the mess approximately goes like this. So this is first of all what we have to look at, but we also have to take integrals over delta 1 and delta 2 here as well, right? In order to marginalize over all density fluctuations delta 1 and delta 2 that give rise to particles being there at positions 1 and 2. But now you see, here is an integral over, here are two integrals over the first two components of the D vector, and they will create us delta functions in T plus S. So we can immediately carry out the delta 1 and delta 2 integrals here. And then we can immediately also carry out the integral over the T1 and T2 components. With the result that only the remaining components, namely those components of the T vector that are Fourier conjugate to the momenta, will be left. And we will have to integrate over the characteristic function now evaluated at minus S1 minus S2 and PP. Okay, that's the result of these delta functions that we get here. But now we can, in fact, insert these quantities into the characteristic function that we have here. Namely, phi, sorry, minus S1 minus S2, minus S1 minus S2 PP. this is, look, we have this quadratic form here, where we have one vector, a transpose T here, whose first two places are occupied by S's, or minus S's. And then we have TP. Then we multiply this with this covariance matrix here, which has density fluctuations in the first 2x2 submatrix. See, this is a matrix that has 1, 2, 5, 8 times 8 components. The first 2x2 are density correlations, or density correlations only. Then above here, we have density momentum correlation. Same here. And here, we have momentum correlation. Now, of course, I'm running out of space, so we need to multiply this with this vector here. Okay, so what do you get? You get an exponential of -1/2 S transpose C delta delta times S. That's what you get from here. Then you get 2 times the cross terms. Right? So you get minus S times C delta P times TP. And you get, what a mess, you get -1/2 TP transpose CPP times TP. Sorry, it's really just sketchy, but nonetheless. And now, you see, now we need to take the Fourier transform with respect to TP here. So we have a Gaussian, essentially a Gaussian in TP, that we have to Fourier transform with a Fourier vector that consists of the momenta here and this cross correlation term. And you know that the Fourier transform of a Gaussian is a Gaussian. So we get a Gaussian now in the momenta minus S transpose times D delta P. And this shifts the whole calculation. You get S dependent terms, and so on and so forth and so on. And then finally, you have to apply the D hat. And then you work all this out, recipe in the lecture note, and the result is stunningly simple. So you see, it leads to Fourier integrals of Gaussians. It leads to Gaussians. It leads to Gaussian integrals. There's no particular complication. It's just lengthy to write down. And at the end, if you then apply the derivatives of the D hat, or contained in the D hat operator, you get, wait a moment, I spoke too fast. Lengthy, boring, not difficult. You get a density, nonlinear free density fluctuation power spectrum, which before looked like this. You recognize this, right? This was the nonlinear free density fluctuation power spectrum that we had before. This is going to change to something with a function capital F that is much, much smaller than 1. But a function capital F that essentially looks like this, so it consists of the density fluctuations. Then it has, if I remember correctly, you have the cross correlations. So this is a cross correlation of density fluctuations with momenta. So this is a vector. You take the scalar product of this vector with k1, you get a scalar. You just add this to the scalar function. Then we have minus c delta p times k1 times t1 squared. Right? That's what you get if you carry out this calculation, whose starting point I sketch and whose details I leave out, and which you can find in the lecture notes. And for all cosmological times that we are interested, now in the distant future, right, several Hubble times in the future, which we are probably not going to be here for, this function f is very much smaller than 1, and we don't care about it. Okay. Does it change the asymptotics of our power spectrum? That's what it could do, right? At whatever amplitude, it could develop, for example, a different type, kind of asymptotic tail if you shift k1 to infinity. And it turns out that it doesn't. And you can now include, in the same way as before, right, in the same kind of analysis that we did before, also the f, capital F, into the asymptotic analysis that we sketched before. And again, the main argument is not changed. And you get the highest power of k still by applying this derivative operator here to the Fourier phase factor and to nothing else. Again, you change the amplitude of the leading order asymptotic term to a value which you will find in the lecture notes, which is complicated and so on. But first of all, the change of amplitude is very small. Second, the asymptotic tail of the power spectrum is not changed. Okay, this is what I wanted to show you. So this concludes what I wanted to say about new material in this lecture. And what I wanted to say today is, first of all, how do you get a velocity power spectrum? This is quite straightforward. Right? You define an operator for the quantity that you need. You apply this operator to the generating functional. You do some simplifications that are suggested by the structure of the generating functional, and you arrive at a result that, if you then apply the asymptotic analysis, leads to the extreme surprise that the density fluctuation, the velocity fluctuation power spectrum falls off exactly like the density fluctuation power spectrum, and completely different from the linear result that you would have expected, or at least I would have. I don't know about you. All right, then another caveat that I wanted to address was that our neglect of initial density and density momentum correlations may also have affected the asymptotic behavior, and it turns out that it didn't. It cannot, because all that taking these initial correlations into account is adding this function f here, and the function f does not change the asymptotic behavior along the same lines of argument that we sketched, neither in the velocity power spectrum nor in the density fluctuation power spectrum. So it seems that this k to the minus 3 fall-off is a rock-solid result, both for velocity and density fluctuation power spectra. And now the next steps. that we have to take but haven't taken yet is to see whether including particle interactions may change or may not change the asymptotic behavior. The mean field approach at least suggests that the mean field term becomes scale independent for large wave numbers, and then it would only change the amplitude of the power spectra, but not the asymptotic tail. And this would be a result not only fundamental for cosmology, but also for all kinds of processes beginning with a Gaussian random field. Because this would mean that then both density fluctuations and velocity fluctuations, regardless of the type of dark matter, regardless of the expansion behavior of the cosmological background and so forth, would lead to structures that become scale independent on small scales or large wave numbers. And the scale independence would only be controlled by the number of spatial dimensions and nothing else, regardless of the dark matter, the type of dark matter, regardless of the cosmological. All right, I would be done. There would be much more to say about different approaches within KFT and so on, but they are so highly technical that I don't think that they are particularly suitable for a lecture yet. I think we have to develop them further because I can clearly speak about them in a lecture. So everything I think that I can meaningfully cover in a lecture is now covered. Thank you. By the way, I had a look at the evaluation of the lecture that you have made, and I was really surprised about how positively you evaluated this lecture. As you know, as I said in the beginning, this theoretical lecture was an experiment because I spoke about all of this for the first time. Right? These are all developments of the past years. And I'm really sure that it must have been confusing in times at times. That's how it is. Thank you for your patience. Other questions? Hey, then I can even leave without having a bad conscience. Good. Thank you very much. As we said before, I will be here next time, next Thursday. I will not cover any new material. I will summarize the lecture and I will be here for your questions. And we stop whatever happens earlier next Thursday, 4 p.m. or end of your questions. Okay, thank you.